Hello, welcome to this video on alternating series. These are basically another type of series for which there is a test specific for them that we can use to test for convergence. And I'll give you an example first of an alternating series. Consider the following. It's the sum from n equals 1 to infinity of minus 1 to the n minus 1 divided by n. Okay, so let's write out the first few terms. So when n equals 1, okay, well, I'll write out the series first with the summation formula. And then n equals 1, this is just 1 over n, right? The negative 1 disappears, so it's just 1 over 1. When n equals 2, well, now it's a negative term, right? It's negative 1 raised to 1. And then the denominator is just 2. And then n equals 3, it's positive again. N equals 4, it's negative. And so on and so forth. Right, so in fact, I can write it like this, just the minus sign down here. And this is an example of an alternating series. As you can notice, the signs alternate between negative and positive. And, well, we already know that the harmonic series, which is the exact same series here but with all positive terms, is divergent. Right? This is divergent by the integral test. Or now you can just say by B series. We already proved that fact. So what happens here if every other term we make it a negative? Okay, and I'll show you what that looks like here. This graph. Remember that we can graph our sequences or our series by just plotting these points on the plane with integer inputs. Right, so n equals 1, it's this point up here, giving you this 1 term. The next term is negative 1/2. So it's going to be down here. And then this is 1/3, 1 over 4, 5, and so on. Right, so this is what the terms of your series looks like. Right, I'm not adding them yet. This is just a graph of a sub n. And you can see that if I graph 1 over x and negative 1 over x, the terms lie exactly, right, on those graphs, on those curves. And that makes sense, right? This just means let's take integer inputs and plot our points alternatingly on the positive and on the negative version of 1 over x. Right, so this is what you're getting. But now the question is, well, we'd like to add these terms up. Right? We're looking at the partial sums. And if the partial sums, if that sequence has a limit, then we're going to say the series converges. So I'm going to draw here, using red circles, the sequence of partial sums. Right? So when n equals 1, the partial sum is just the first term. That's why they coincide here. When n equals 2, well, a sub 2 is minus 1/2. But the second partial sum is a1 plus a2. So the first two terms here, 1 minus 1/2 is exactly 0.5. Right? So that's why this is up here. This is positive 1/2 for the second partial sum. Third partial sum, well, it's up there, right? You added 1/3. That's the third term. 1/2 plus 1/3, that's 5 over 6, about 0.83. And we can keep going. And we see from the graph here that it also appears as though our sequence of partial sums approaches a finite number. Okay, well, that's good. Right? We have a guess here that this series is convergent. So I'll write that down here. guess the series converges. Now, how are we actually able to show this? Well, it turns out that we only actually require two conditions to hold in order to conclude that an alternating series converges. Okay, and you may be able to see it from this picture here. I mean, there's a pretty obvious condition that has to be true, right? The green axis down here, which is your original sequence of a sub n's, that has to approach 0, right? I mean, that's basically your test for divergence. What else, though? The magnitude of these green x's has to also be decreasing, so that at each step here, in the sequence of partial sums above, in the red circles, every time I add a term and I subtract the next term, then I add and subtract, I should be adding and subtracting something that gets smaller and smaller and smaller. Right? And that way, my series is going to converge. My sequence of partial sums is going to converge. And so that is formalized here in the statement of what we'll call the alternating series test. Right? So an alternating series, again, that's any series whose terms are alternately positive and negative. And so usually, we'll denote alternating series in this way, where this b sub n term denotes the magnitude of each term. As if you ignore the sign, right, of each term, it's whatever positive part is left. So in this previous example, b sub n is just 1 over n. Well, what does this say? Well, b sub n, that sequence has to be decreasing. Right, that's what this says. bn plus 1 is less than or equal to b sub n. Also, b sub n has to approach 0, which is, again, those two conditions that I mentioned when I showed you the graph a while ago. It turns out if both these conditions hold for b sub n, then you can conclude that the series converges. And you're done. Nice, it's a nice result. And we can actually use it now for this initial example. Right? First, is it true that bn plus 1 is less than or equal to bn? Yes. Simply because n plus 1 is larger than or equal to n. And we can now say 1 over n plus 1 is smaller than or equal to 1 over n. Right? So that proves this sequence of bn's is decreasing. Finally, is it true that bn approaches 0? Clearly, yes. It's 1 over n. And now we're able to conclude by the alternating series test this series converges. Now, really the idea behind the alternating series test is the following. Right? Again, two conditions, right? Bn decreasing, Bn approaches 0. If you look at our graph here again, this sequence of partial sums up here, these red circles, if Bn approaches 0, well, okay, so that's what we need, first of all, for the test for divergence. But the fact that Bn plus 1 is always smaller than Bn means that it's the gap here in between the upper portion and the lower portion of the partial sums. They're going to converge to the same number. I mean, what are these points up here? These are the odd partial sums, right? This is S1 S3, S5, and so on. While the points below are the even partial sums when you stop at an even term. This is S2, S4, S6, and so on. And so the whole reason why this works is because if you treat each part here, the even sums and the odd sums, as a separate sequence, right? Only take the top or only take the bottom, then these are actually bounded and monotonic sequences. So we know they're going to converge. And we know that they're going to converge to the same number because this Bn goes to 0, right? Bn is whatever you're adding or subtracting to get to the next partial sum. Right? And so that's the rationale. That's the idea behind why the alternating series test works. And I'll just end here with another example. Determine if this series converges or diverges. Sum n equals 1 to infinity, n cosine n pi over 2 to the n. Okay, so at first glance you may be like, well, is this actually an alternating series? Can I use the alternating series test? Well, it's cosine n pi, right? You know what the value of cosine of n times pi is equal to. It's equal to -1 if n is odd, and 1 if n is even. Right? Just alternates between 1 or -1. Pi is here, and then 2 pi, and then 3 pi, and then back to 4 pi, and so on. So really, I can write the series as n minus 1 raised to n over 2 to the n. Right, so this is alternating with the positive part, b sub n, equal to n over 2 raised to n. Okay, so let's check. Is it true that bn plus 1 is smaller than or equal to bn? So how do you prove this is decreasing? Well, you can play around with some inequalities. But I'll show you something you have seen before. Right? If you just use calculus, construct a function f of x, x over 2 raised to x, and then take its derivative. Right? In fact, I can write this as x times 2 to the minus x, just so I can use the product rule instead of the quotient rule. Okay, so this is 2 to the minus x plus x, and then what's the derivative of 2 to the minus x? So that's 2 to the minus x times ln 2 times -1. So this is equal to now 1 minus x ln 2 divided by 2 to the x. And from here we can see that this is actually negative if x is larger than 1 over ln 2. Okay. Remember that for our series, sometimes we don't really need our series to be decreasing the whole way. Like, it can increase the first few steps, or in our sequence, it can increase in the first few steps and then start to decrease forever. Right? So the derivative here is actually positive when x equals 1, right? When n equals 1. But that's fine, right? When n equals 2, well, I don't know what ln 2 is equal to. Let me get my calculator here. What's ln of 2? So 1 over ln of 2 is actually 1.44. Right? So for all values of n larger than or equal to 2, this is decreasing. And that's good enough for us. Okay. How about the other condition? So what was the other condition? What's the limit? As n goes to infinity of b sub n. Well, we just have to show it's 0. And if we do, we can conclude that the series converges. Okay, so what is this equal to? Well, that's equal to 0. since if you look at your corresponding function in the reals, you can use L'Hopital's rule since it's an indeterminate form, infinity over infinity. This goes to 0. And it's very reasonable, right? You have a linear function, you're dividing by an exponential in n, which grows so much faster than your numerator, right? So your fraction definitely is going to go to 0 there. Therefore, by the alternating series test, this is a convergent series. Now, what I'd like you to start thinking about is, if one of these two conditions fails, either it's not decreasing or b sub n doesn't approach 0, can you conclude that the series diverges? Okay. I mean, if bn does not go to 0, in that case, it's actually easy to say that it diverges because it fails the test for divergence. And so really what I want you to think about is, if bn is not decreasing, can you conclude it's divergent? And so I'll leave you with that question.